Yeah, so um, we're going to start a chapter called as Semiconductors. This is in the mains syllabus. And personally, I found that this is like one chapter which uh, a lot of students maybe struggle to really understand. Yes, acha, wait. So can we skip the MP at the time of board exam? I mean, yeah, don't worry about that. Focus on your boards because see, what is the MP this time? It's going to be a full test, right? And you're going to give a lot of full tests after this as well. You're going to PACE is going to have a series of full tests one after the other. So if you feel that you're not well prepared for your boards and you want to focus on um, doing the boards well, my suggestion is yes, go ahead. You can give the boards. You can skip the MT. You can prepare for the other test. That's fine. Okay, um, if you if you want, just for practice sake, if you want to give the MT like that without having to revise too much, just to see where you stand. If you have that kind of time, you can go ahead and give the test. Okay, but again, that's going to take even the test itself may take 6 hours of your time, right? So even if you skip it, it makes sense. That's fine. And in just in a few weeks of giving your board exams, you're not going to forget everything you've been studying for the last 2 years. So it's fine if you want to take a break. All right. If you do take a break and lectures are going to continue, please just make sure that you at least um, refer to these lectures later. So especially talking about semiconductors, this is one such chapter that I found most students normally struggle with. And there are a couple of textbooks people can read, but then even the textbooks after a point, somewhere or the other, certain things maybe don't make sense. You're not able to understand them properly. So I believe the notes that I'm going to make are made an extra set of notes. Not everything here is absolutely important, but certain things over here are going to be there for your reference. So it's like I'll point out to you what things are there only for reference. So if there are certain doubts that you have, how this works, how that works, my notes in a way will be like the textbook you can always refer to get your doubts cleared. Okay. Um, this is from a mains perspective an important chapter. Yes, normally is a question lagbhag aata hi hai. So you should not ignore it. Okay? It's good to understand it once. Once you pay attention, once you understand, you'll more or less get the idea. Just a second. Just a second. Yeah, sorry, guys. Sorry. I had some work. I didn't say anything. Don't worry. I just stepped aside. Um, should we attend PACE lectures during the board exams? Guys, if you want to prepare for your board exams, if you feel you need the time, okay, then please do that. That's fine. But make it a point to then cover up. Okay, once you're done with your boards, put in those extra hours and cover up all that you missed. Okay, you're going to miss quite a lot because right now I see your timetable is packed, right? So lot of lectures are going on right now. So take a judgment call. If there are days where there are gaps, try to attend lectures and try to reduce the number of lectures you miss. Okay, थोड़ा attend कर सकते हो कर लो, but somehow you can cover up. Okay, the cover up time, you may not be able to cover up in a week. It may take even more than 2-3 weeks. Then that's fine. Just do that, because I'm sure what is going on now are some crucial chapters. Okay, so please do that. They should ideally give some holidays. You can raise that issue. Please tell your center managers as well. Okay, they should at least for you guys ideally give some holidays, because yeah, it doesn't make sense. It just, right now at least 20 people are there. I can sense next week 4-5 ही लोग रहेंगे. So it of course does not make sense. So they should ideally give some holidays. Let's see. Cool. So let's get started with semiconductors. Okay. So energy bands in solids. So as we saw in the boards, I'm going to go a little fast. A lot of these points are theoretical. Just, if you have any doubts, just please feel free to ask. Ask me to explain things again. Okay, and I'll do that. But otherwise, we just read through these things together. These are collected from various sources, not just HCB or NCRT. A lot of things were not perfectly explained, so a lot of research had to be done to Google and other sources as well. So finally, these notes are there for your reference. Okay. Energy bands in solids. So we're going to start with the simple idea that we know that electrons in isolated atoms typically occupy discrete energy levels, as you've seen in your Bohr's atomic model. Okay? Discrete energy levels, minus 13.6, then minus 3.4 electron volt, and so on. But what happens is when these same atoms, they come close to one another, and occupy a crystal lattice, as you're probably learning right now in solid state. Okay? As they occupy different lattice structures, these discrete levels spread out into energy levels with continuous variation called as energy bands. So no longer are the energy levels discrete in this manner. Okay, even if you imagine two s orbitals coming close to each other, there may be times in the s orbitals when एक atom का s orbital और दूसरे atom का s orbital वाले electrons are close to each other. Okay, so there may be a time where they're closer, right? And when they are closer, the potential energy will, the energy will be higher. Right? We're talking about electrons being close. Electrons don't like being close to each other. So there may be a time when they're closer to each other, and tab energy is above average. There may be a time where they are further away from each other. Okay? And when they're further away from each other, the energy is below average. So as you bring several atoms closer to each other, we're no longer talking about isolated atoms, but atoms in a solid crystal structure. What happens? They don't have single discrete energy levels. They have energy bands. Okay, so this could represent the 1s energy band. That could represent the 2s energy band, and so on. So they have energy bands that are formed. Okay, there's a continuous variation of energy possible for that orbital. Then moving on. Out of all these energy bands, we are only interested in 2 bands. We're not interested in what happens in the inner shells, but what we are interested in is the energy band, which includes the energy level of the valence electrons, is collectively called as the valence band. Okay, so all the electrons in the outermost shell, the energy band that those electrons can occupy is called as the valence band. In this valence band, if the electron is in that band, okay, we'll say that the electrons are still bound to the respective atoms. Okay, so the valence band is that last topmost energy level where the electron is still attracted to the atom. Okay, still attracted to the atom, and in this way still a prisoner, bound to that atom, a prisoner of that atom. But then there is an energy band above the valence band. The energy band above the valence band is called the conduction band. The electrons in this, I'll show you a diagram very soon. The electrons in this conduction band are free to move away from their parent atom. And these are the electrons which are responsible for conduction. Okay, so there's a conduction band above the valence band. If an electron jumps to the conduction band, they are free to move away from the parent atom. If the electrons stay in the valence band, they are bound to the parent atom. Okay, that's the basic idea. The gap between the valence band and the conduction band is called as the energy gap or band gap or energy band gap. Okay, I mean, these are all alternate names: band gap, energy gap, या energy band gap. ठीक है, and उसके लिए एक छोटा सा symbol है EG. ठीक है, energy gap, not example, EG, energy gap. So that's the symbol for it. Let me show you a diagram of how this looks. All right, so over here in all these diagrams, नीचे the red band is a depiction of the valence band. Okay, this represents energy, just like Bohr's atom में, right? First level ये ground state energy हो गया, फिर first excited state energy, फिर second excited state energy, है ना? तो isolated atom में कैसे discrete lines है, अब हम क्या बोल रहे हैं, अब bands है, ठीक है? Bands है, instead of lines you have the energy spread out. ठीक है, the energy is spread out over from one level to another level. ठीक है, there's a maximum and minimum energy and there's a continuous spread of energy in that particular band. ठीक है, अब इसमें क्या है, in metals we see that the valence band and the conduction band overlap. What is the consequence of this? Okay, the valence band and the conduction band overlap, allowing valence electrons to easily enter the conduction band and be available for conduction. So because there is no band gap between the valence band and the conduction band, electrons which are in the valence band can easily also enter the conduction band. Again, they don't need to jump. They don't need extra energy to enter the conduction band. They can directly go into the conduction band. And once they are in the conduction band, they are free to move away from the parent atom. And that's why we say in metals, the electrons that are present are free electrons. Okay, if there is a slight electric field through the metal, the electrons will move in the direction, or rather opposite the direction of that electric field, right? So they are free to move away from their parent atom. That's how charge separation takes place in a conducting material, in a metallic material. Insulators, mein, the band gap is very large. Just to give you an idea, it's of the order, it's greater than 3 electron volts. And in these insulators, the electrons stay bound to the atom and are therefore not available for conduction. Just giving an example, diamond, like diamond has a band gap of 5.5 electron volts. So what is going to happen? The electrons are going to stay attached to the parent atom, right? And the amount of energy they need to jump to the conduction band, that amount of energy is too large. Again, they don't get that kind of energy, even with collisions that may take place due to kinetic energy, because of the temperature diamond may have. Okay, even more energy is not enough to make electrons jump to the conduction band. So the electrons are all bound to the parent atom if this gap is too large. Okay, you can imagine the conduction band as a conveyor belt. Interestingly, that's also CB, conveyor belt. So once the electron jumps there, it's free to move away from the parent atom. In semiconductors, the band gap is finite, but a lot smaller than those for insulators. The band gap is not zero. Okay, it is going to be finite. It's going to not be infinitesimally small. There is still a significant band gap, but they are smaller than those for insulators. Okay? At temperatures above 0 Kelvin, what will happen is thermal collisions may impart enough energy for electrons. So above 0 Kelvin, you have kinetic energy of the molecules. Below, you don't have any. I mean, at 0 Kelvin, you don't have any kinetic energy, but above 0 Kelvin, you have the molecules having their own kinetic energy. Greater temperature means molecules vibrate with greater energy. So because of this vibrational energy, it's possible through this process to have enough energy imparted to electrons so that they can jump from the valence band to the conduction band and thus be available for conduction. So all the electrons are not going to do this. In fact, very few electrons will do this, but still a few be but some electrons will still at least by chance happen to do this. So in silicon, the band gap is 1.1 electron volt. Germanium, it's 0.7 electron volt. Compare that with carbon, which we said was 5.5 electron volt. So silicon and germanium are examples of materials that are commonly used as semiconductors because their band gap is very small. Okay. I hope you guys understood the play of band gap. So what happens now as electrons jump from the from the valence band to the conduction band? Let me just check that out. So in unexcited state, the conduction band of insulators, and yes, unexcited state, okay, ground state conduction band is of semiconductors and insulators is 0. Yes. Okay. And over here also we are, in a way, we're talking about excitement that is coming from temperature itself. तो अलग बात है कि if I give sufficient light to these guys, इनको भी हम in a way excite करा सकते हैं. ठीक है? We're not talking about that. We are in a way focusing on electrons jumping to the conduction band by temperature itself. So the band gap being significantly smaller, ठीक है? Temperature के कारण an electron can jump to the conduction band in a semiconductor. But yeah, just to answer your question, typically unexcited statement, they'll all occupy the lowest possible energy level. All right. Now, let's talk about intrinsic semiconductors. Okay. So, what's the definition, by the way? Tetravalent elements. See? So, group 4 of your periodic table. Those elements like silicon and germanium, which do not have any impurities in them, are called as intrinsic semiconductors. Okay. So, normally silicon, germanium without any impurity, intrinsic more has to do with something which is pure, which does not, you're going to very soon see that we will intentionally add impurities to these semiconductors. But for semiconductors which have no impurity in them, they are intrinsic semiconductors. And classic examples are silicon and germanium. So these guys have a diamond-like crystal. In solid state, the crystal structure is similar to that of diamond. And what is a crystal structure like? Each atom has 4 covalent bonds with 4 other atoms, right? So each atom has 4 covalent bonds with 4 other atoms. And the actual structure is a tetrahedral structure. Okay. The diagram I'm going to make below, it's not easy to draw the tetrahedral structure. So the diagram I've made and what you may find in most books is like a, in like a square planar type of diagram. But technically, these are not all in one plane. This is actually a tetrahedral structure. Okay? So as temperature increases, above 0 Kelvin, thermal energy becomes available for electrons, as we said, to break away from the valence band and enter the conduction band. The neighborhood from which the electron comes out, पूरा चैप्टर में ऐसा ही थियरी है क्या? क्वेश्चंस भी है, थियरी भी है. ठीक है, ये थियरी मतलब थियरी में you don't have to memorize anything and spit it out later. ठीक है, it's not like what you're going to do for your boards. रटना नहीं है, एक बार समझना है. Once you understand, like, okay, this is what happens, then certain things will stay in your head. Okay, so but हाँ, मतलब काफी वैसे it's something brand new, so something unlike anything you've seen before. So in that way, even to just understand what is happening and why things are happening, theory is going to be needed for this chapter. Okay. the neighborhood from where were we? Okay, so as the temperature increases above 0 Kelvin, yeah, it enters the conduction band. The neighborhood from which the electron comes out is left with a vacancy called as a hole. Okay, so electron जहां से निकला, वो neighborhood is left a vacancy. So that vacancy is going to be called as a hole. Okay, I'll show that on the next page. The hole is said to be effectively having a positive charge. Okay, the hole is said to effectively have a positive charge of plus E. This is what normally people say. Technically, though, it's not the hole, it's the atom that the hole belongs to that has the positive charge, as those atoms will have one extra proton than the number of valence electrons. So let me just show you this. Let me explain the statement with the diagram. So imagine this is our silicon crystal structure. Okay, and it doesn't look like this. This is a simplified diagram. Reality mein, every single silicon atom has a tetrahedral configuration. Okay, it has a tetrahedral configuration. Now, what is happening is if this silicon crystal exists above 0 Kelvin, exists at room temperature, because of thermal vibrations, electrons in the valence band are those which are still attached to an atom, okay, or which are being shared between a pair of atoms. So those electrons in the valence band are going to get excited and they're going to enter the conduction band. तो मैंने बस ऐसा conduction band ऐसा separately draw किया in a way to imply कि अब electron is no longer bound to this guy. The electron is free to move. So in this process, we have an electron hole pair generation. Electron यहाँ से निकल के एक conduction electron बन गया, free electron बन गया, but वो जहाँ से निकला वहाँ पे एक vacancy create किया, which is called as a hole. Okay, so an electron was supposed to be there, it's not there. This electron has, of course, a charge of minus E, and people normally say it's accepted. You can say that a hole has an effective charge of plus E, but reality mein, what is the hole actually? The hole is just the absence of an electron. So technically, वो plus E charge किसके पास है? तो ये silicon atom, जिसमें if you see technically neutral silicon atom में 4 इलेक्ट्रॉन होना चाहिए, है ना, 4 इलेक्ट्रॉन होना चाहिए. अब फिलहाल इसके पास 3 इलेक्ट्रॉन है. So technically the positive charge lies with this silicon atom, which has one more proton than the number of electrons. So that's where the positive charge is really. Okay, so when I say hole has positive charge, technically means the atom which to which that hole belongs has the positive charge. The atom which has lost the electron has the positive charge. Abhi, imagine ki now if we apply an external electric field, okay, external electric field towards the left. So electrons move opposite the field. Negative charge moves opposite your electric field, as you know. Positive charge moves in the direction of the electric field. So electrons kya karenge when I apply this external field? The electrons are going to go in that direction, opposite direction. तो conduction electron जो है free to move, वो opposite direction में चला जाएगा. अच्छा, ये opposite direction में जाने के कारण electron के motion के कारण एक current आ जाएगा, and current will be opposite the direction of flow of the electrons, as you guys know already. So because of the movement of the electron in response to this field, there is a current in the direction of my electric field, and then let's call the current as IE. So that's the current due to the electrons. Electron का conduction electron का motion का current is IE, और ये सब कहाँ पे हो रहा है? Conduction band के अंदर हो रहा है. ठीक है? This is what you normally see in metals. Now, what is also going to happen is, because of this electric field, look at this electron. This electron would also want to move away in the opposite direction of this electric field. तो ये electron क्या करता है? ये electron conduction band के अंदर ही, मतलब valence band के अंदर ही रह के, it just moves to this spot. ठीक है? This electron moves to this spot. As it moves to that spot, what basically happens is the hole now is over here. So the hole which was over there has now moved towards the left. So effectively we say this is as though the hole has moved in the direction of my electric field. So the holes move in the direction of the electric field, electrons move opposite to the electric field. ठीक holes इस direction में जा रहा है and holes effectively have a positive charge. तो hole इस direction में आने के कारण we are saying कि our current, there is now a current towards the left. There is now a current towards the left. There is now a current in the direction of the electric field. ठीक है, बाहर से तुमने इलेक्ट्रिक फील्ड डाला, ये बैटरी कनेक्ट किया जो ऐसा इलेक्ट्रिक फील्ड क्रिएट कर रहा है, तो होल इलेक्ट्रिक फील्ड के डायरेक्शन में जाएगा वैलेंस बैंड के अलोंग. फ्री इलेक्ट्रॉन्स इलेक्ट्रिक फील्ड के ऑपोजिट डायरेक्शन में जाएंगे कंडक्शन बैंड के अलोंग. बट दोनों के कारण करंट सेम डायरेक्शन में होगा. होल तो पॉजिटिव है तो वो जिस डायरेक्शन में जा रहा है उस डायरेक्शन में करंट है. इलेक्ट्रॉन नेगेटिव है, राइट, तो उसके ऑपोजिट डायरेक्शन में फिर से करंट आता है. तो यू कैन सी हाउ बोथ द इलेक्ट्रॉन का करंट एंड द होल का करंट आर इन द सेम डायरेक्शन. एंड इन द सेमीकंडक्टर, conduction takes place both because of electrons moving along the conduction band and holes moving along the valence band. Right? Any doubt so far? Okay, nothing. All right. So the net current, okay, the net current is the current due to the electrons plus the current due to the holes. So the net current is the addition of those two. Okay, very obvious idea. Now another important relation that we normally see is that the number of electrons into the number of holes is technically a constant for a given semiconductor at a particular temperature. The number of electrons, Ne is actually not even number of electrons. Ne is number of electrons per unit volume. So let's use the word concentration. Concentration of electrons into concentration of holes is a constant for a given semiconductor at a particular temperature. Okay, I can explain. I mean, this is a fact that is known. I can somehow just maybe explain it to you guys why this happens. Okay, so why is this product always a constant? Okay, तो यहाँ पे ये जो पहले ये ब्रैकेट में नॉट इम्पोर्टेंट वाला पार्ट जो लिखा है, जस्ट एक्सप्लेन दैट. ये सिर्फ तुम्हारे अंडरस्टैंडिंग के लिए, यू डोंट नीड टू रिपीट दिस इन फ्रंट ऑफ एनीवन एल्स. फॉर योर अंडरस्टैंडिंग व्हाई इज दिस प्रोडक्ट अ कांस्टेंट. तो जल्दी से एक बार समझा देता हूँ कि रियलिटी में दो चीज हो रहा है. एक चीज जो हो रहा है दैट द एटम, ओके, is getting converted into electrons and holes. Like, okay, atom is basically producing an electron hole pair. So electron hole pairs are continuously being created, but the rate at which this reaction takes place, the forward rate of the reaction, is a constant. It's not going to depend on the number of atoms. And why does it not depend on the number of atoms per unit volume? Because the number of atoms per unit volume is more or less fixed in the crystal, right? That doesn't even change. Even if it depends on the number of atoms per unit volume, we don't see that change, right? That's not going to change. Concentration of the number of molecules of the parent atom per unit volume is more or less going to be fixed. Zyada change hoga hi nahi. All right, so does not depend on the number of atoms per unit volume in the crystal. However, this rate that we mentioned, it's found to increase with temperature. Because greater the temperature, the easier for that electron to jump to the conduction band. So this rate will, of course, this Kf wala term will depend on temperature. Okay? The reverse reaction जो होता है is when electrons and holes that are already present, they also can recombine and they can again disappear, right? They can recombine and form the original atom. ये backward reaction का rate should depend on the concentration of electrons and holes. Obviously, जितना ज़्यादा electrons होगा, जितना ज़्यादा holes होगा, right? उतना ज़्यादा उनका probability of meeting and annihilating each other. So backward reaction का rate is dependent on concentration of electrons and holes. Now at equilibrium, At equilibrium, forward rate and backward rate are equal, right? That's when the number of concentration of electrons and holes doesn't change any further. So at equilibrium, forward backward rate are equal. Okay. What equation does that give us? Kf is equal to Kb into concentration of electrons, concentration of holes. वहां से आता है concentration of electrons and concentration of holes are actually उनका product is going to be a constant. Okay, so that's an important idea. ये बस explanation था. You don't have to see this again. You don't have to repeat this in front of anyone again. But just to satisfy the mind and tell why this product is a constant, I've in a way explained it. So it's a constant, but I'll try, baby. I'll try. Okay, it's a constant, but it increases with temperature. जितना ज़्यादा temperature होगा, उतना easily electrons and holes produce होगा. Okay, so therefore the product of number of electrons and number of holes is a constant. We're going to call that constant Ni ka square. We're going to call that constant Ni ka square, and this constant increases with temperature. जब मेरे पास एक इंट्रिंसिक सेमीकंडक्टर है, हम एक्सट्रिंसिक में देखेंगे क्यों इलेक्ट्रॉन्स का नंबर एंड होल्स का नंबर सेम नहीं होगा, बट इंट्रिंसिक अभी जो हमने देखा, we saw a silicon atom create an electron and a hole, right? So for that simple kind of conductor, number of electrons and number of holes should be the same. So concentration of electrons and concentration of holes should be the same. So on that note, concentration of electrons should be Ni and concentration of holes also should be Ni. So Ni actually represents the number of electrons or holes in the intrinsic semiconductor. Okay? Intrinsic semiconductor में number of electrons and holes बराबर होता है, and that number is Ni. I think it's also referred to as Ni. Number of holes in an intrinsic semiconductor. This is also the number of total charge carriers by 2 divided by volume by 2. क्योंकि total charge carriers कितना होगा? Number of electrons plus number of holes. All right. So what we are saying, intrinsic semiconductor में number of electrons and holes बराबर है. उन दोनों का double total number of charge carriers है. Because charge carriers are both electrons and holes, and they are equal in number. Therefore, number of electrons is half the total charge carriers, and the remaining 50% of total charge carriers are your holes. See? Any doubt on this page? Yeah, this you're not going to read again. This is again just for your reference why that product is a constant. Okay? I've just explained it with the idea of equilibrium. Okay. All right. So conductivity in a metal or conductivity in a semiconductor, how does that look? All right. Again, this is just for your reference. In case you would need this, there is a word over here called as mobility. So I'll just in a way explain that. Ohm's law के हिसाब से, you know that conductivity is the current density upon the electric field, J by E, right? And that's Ohm's law. Current density is current by area, right? So you have conductivity is I upon area into electric field. Current can be written as NEA into drift velocity. Okay, NEA, right? Number of current where metal में charge carriers is the number of electrons, free electrons. The number of free electrons into E charge into area into VD. Area काट के what you're left with is NEVD by E. ये जो drift velocity by electric field होता है, that is called as mobility. How fast you move under a given electric field is mobility. So I just thought I'll just mention this. I saw this in the HCV, it's not in the NCRT, so may not be very important, but again, just for your information, back of the mind में, just remember that drift velocity by electric field is referred to as mobility. More importantly, semiconductors के context में इतना ही बोल रहा हूँ कि semiconductors के context में you have two charge carriers. You have electrons and you have holes. Electrons के कारण कंडक्टिविटी आ रहा है नंबर ऑफ इलेक्ट्रॉन्स पर यूनिट वॉल्यूम into E into mobility of an electron. And by the way, when I say electron, I will always mean the conduction electrons, not the ones which are bound to silicon. The ones which are bound to silicon are not contributing to current. The ones which are free, which have moved away, broken free from the parent atom. Okay, those electrons के बारे में बात कर रहे हैं. तो उनका concentration per unit volume, concentration into charge into drift velocity by E, यानी कि mobility is इलेक्ट्रॉन का कंडक्टिविटी. एंड सेमीकंडक्टर में होल्स भी मूव करते हैं, तो अकॉर्डिंगली होल्स के लिए भी तुम डिफाइन कर सकते हो नंबर ऑफ होल्स पर यूनिट वॉल्यूम इनटू उनका चार्ज का मैग्नीट्यूड व्हिच इज अगेन E इनटू द मोबिलिटी ऑफ अ होल. So just यहाँ पे like the only take back is conductivity in a semiconductor is going to be because of electrons as well as holes. The other take back is just remember in the back of your mind, mobility is drift velocity by electric field. And somewhere also just remember कि electrons का mobility is more than holes. Electrons का mobility is more than holes. It's just they move a little faster than holes do. Because holes के movement में one electron still needs to in a way somehow break slightly free from one atom and go to another atom. So there is a little bit of activation energy that somehow reduces the rate at which holes move. But in the conduction band, electrons are free, so they can move more easily. Okay. Any doubt in this? Yeah, again, just mentioned it here. Every time you read बस एक बार ये तुम देखोगे back of the mind में रह जाएगा कि electrons move a little faster, और ये भी रह जाएगा कि mobility क्या होता है. That's not a critical concept. It's just again for your reference. Now, extrinsic semiconductors. Now we are coming to the more important part. So we find कि a pure intrinsic semiconductor, we find that a pure or intrinsic semiconductor का conductivity, as I said, depends on the temperature. Because जितना ज़्यादा temperature, उतना ज़्यादा number of electrons and number of holes. But it's still found कि at room temperature, this conductivity is very low. This conductivity is quite low at room temperature. It's not enough. There are very few charge carriers because room temperature में वो vibrational energy उतना नहीं है कि easily electrons and holes create हो जाए. It's not enough. Yes, so that's why you have a very low concentration of electrons and holes. However, when a small amount, let's say a few parts per million of a suitable impurity is added, its conductivity is increased manifold, and we'll see how. The addition of these desired impurities is called as doping. Okay, so the addition of these desired impurities is called as doping, and the impurities added are called as dopants. Okay, the impurities added are called as dopants. Okay, such materials are called as extrinsic semiconductors or impurity semiconductors. So over here, I just normally crack this joke. Why did the extrinsic semiconductor cut short his vacation to just 2 days? Why did the extrinsic semiconductor cut short his vacation to 2 days? It's a really sad joke. The answer is because he had dopants, pants. Okay? He just had 2 pants, and he ran out of clothes, so he had to cut short his trip. Anyways, but extrinsic semiconductors have these impurities which are going to increase the conductivity. What are these impurities? ऐसा क्या हो रहा है जादू impurity डालने में? तो वो अब समझेंगे. ठीक है? तो पहला जो extrinsic semiconductor है, that's called as a p-type semiconductor. Okay, p-type semiconductors में dopants are trivalent atoms. For example, boron, aluminium, gallium. Okay, these kind of atoms. Now, compared to silicon, these atoms have only one electron less. Okay, they already have just 3 electrons in the outermost shell, so they have 1 electron less. So wherever they are, they're going to behave as holes. Okay, look at this diagram. Ye apna silicon hai. Imagine your silicon lattice. Each silicon atom is, giving 1 electron to its neighbor and thus forming 4 covalent bonds by sharing. But consider उन सब के बीच में suddenly एक aluminium atom है. वो तो technically 3 ही electron share कर पा रहा है, and यहाँ पे with the fourth bond 1 electron is missing. So that 4th bond of aluminium behaves like a hole. Okay, so these can now what can this hole do? What can technically these atoms do? They can accept electrons from neighboring atoms and are thus called as acceptor impurities. Okay, they can accept electrons from neighboring atoms, so they are called as acceptor impurities. यहाँ से silicon का एक atom जाके aluminium का hole उधर भर सकता है. So that's how in a way holes can move to the left or to the right जब बाजू वाले atom से electron आके उस hole को भर देता है. Therefore, this type of conductor is called as an acceptor, or this type of impurity is called as an acceptor impurity or an acceptor dopant. Okay? Now, the number of holes per unit volume is in this going to be more or less equal to the number of impurity atoms per unit volume. तो हम इसमें normally क्या करते हैं, impurity atoms थोड़ा काफी हद तक काफी डाल देता है, in the sense कि this number of impurity atoms is going to be a lot more than the number of holes you could have had naturally. Okay? The number of impurity atoms present will be a lot more than the number of holes you could have had naturally. Intrinsic semiconductor में है ना, ज्यादा conductivity के लिए इसमें हम ज्यादा impurities डाल सकते हैं, and जितना impurities डालेंगे लगभग उतना number of जितना जैसे aluminium, boron, gallium atoms डालेंगे उतने ही holes रहेंगे, लगभग उतने ही holes रहेंगे जितना p type impurities है. Now, because of this क्या होगा, since the product of the concentration of holes and concentration of electrons is a constant, it's still the same constant. Temperature same रहेगा, base metal same रहेगा, silicon है इधर base metal, so that product Ne into NH is still a constant. Okay, it's still a constant. ठीक है, aluminium डाल के हमने फिलहाल NH बढ़ा दिया, but NH into Ne constant है, तो क्या हो जाएगा, number of electrons per unit volume कम हो जाएगा. Okay, number of electrons per unit volume कम हो जाएगा. तो क्या होता है actually, the rate at which electrons and holes are going to be produced afresh, that is still the same. ठीक है, टेम्परेचर के हिसाब से some electrons and holes may keep getting produced. But अब इधर क्या है, बहुत सारे holes आ गए aluminium के कारण. तो because aluminium के कारण इतने holes आ गए, the chances of whatever electrons are present, the chances of them combining with so many holes increases. So वो electron and hole का recombination जो होता है, that reaction rate increases because इतने holes are present. And therefore जो वैसे पहले से electrons जितने होने चाहिए थे अब उससे कम है, because they keep colliding with the hole and disappearing. So you have a lot of holes, but you have very few free electrons in this type of semiconductor. तो इस type of semiconductor में we thus call holes as the majority charge carrier. Majority, both electrons and holes are charge carriers. Majority charge carrier is the one which is more in quantity, जो ये supply कर रहा है. तो holes are the majority charge carriers, electrons are the minority charge carriers in a p-type semiconductor. And sometimes क्या होगा, you may know all your concepts, but exam के बीच में एक बकवास सा doubt आएगा, which is the p-type? Is it aluminium or is it, we're going to see group 5 as well. Group 5 ये tetravalent है, ये trivalent है, and n type एक और semiconductor होता है जिसमें pentavalent atoms होता है. तो बेकार का एक ऐसा doubt आएगा एग्जाम में कि which is the p type कौन सा है, is it group 3 or is it group 5, right? So the way you remember is, just remember that p stands for positive, holes are positive. So p-type semiconductors are ones which are in a way supplying holes, increasing the number of holes. Okay. Yeah. Let me just see this down. So can I please explain why the number of electrons per unit volume decreases again? Absolutely. Explain that. Okay. So यहाँ पे just to again refer to this, क्या हो रहा है really, है ना, दो चीज हो रहा है. एक तो atoms, एक ये rate हो रहा है कि atoms are producing electrons and holes, and that has to do with temperature, है ना. Just because of the vibrational energy, there is a chance, there is a probability of an atom producing electrons and holes. तो ये reaction होते जा रहा है. और ये दूसरा reaction is a reaction where the existing electrons and holes recombine to create neutral atoms. So basically they disappear, they annihilate each other. Electrons and holes annihilate each other. Now क्या हो रहा है? When I place aluminum dopants, group 3 dopants, which increase the number of holes significantly, they do not affect this reaction, because this reaction depends on the vibrational energy, depends on the temperature. Okay? So this reaction is not affected appreciably. Okay? Number of silicon atoms per unit volume is still large. It's still the majority metal. The majority, I mean, that's still large, okay, in quantity. So, क्या हो जाता है? So this is not affected that much. ये rate of producing electrons and holes is not affected. But what gets affected is this rate. Okay? This rate of electrons and holes recombining gets affected. क्यों? Because अभी बहुत सारे holes हैं. तो पहले तो इलेक्ट्रॉन एंड होल का रिकॉम्बिनेशन का चांस बहुत कम था, क्योंकि इलेक्ट्रॉन्स कम थे, होल्स कम थे. अभी होल्स बहुत सारे हैं. ठीक. So the probability of them colliding and annihilating each other increases. So the backward reaction increases. तो इसके कारण electrons in a way disappear. Okay? It's just like तुम्हारा chemical equilibrium. ये जो अब equilibrium reaction है, तुमने अब ये प्रोडक्ट, ये जो प्रोडक्ट बन रहा है यहाँ पे, इसका कॉन्सेंट्रेशन बढ़ा दिया, है ना, तो the reaction will go towards the left hand side. Number of holes suddenly बढ़ाया तो it will go back to the left hand side. तो जितने से होल्स बढ़ गया वो थोड़ा सा कम होगा, बट इलेक्ट्रॉन्स काफी हद तक कम होगा. It's like constant, if I remember my chemistry correctly, concentration of H plus and concentration of OH minus, the product is 10 power minus 14, right, at whatever room temperature. You increase the concentration of H plus in an acid, OH minus automatically कम हो जाएगा, product 10 power minus 14 रहेगा, right, and vice versa. Base में increase OH minus concentration, तो H plus कम हो जाएगा, yeah, and accordingly pH बढ़ जाएगा, but product उनका 10 power minus 14 रहेगा. All right. Yeah. So we were at P-type semiconductors. यहाँ पे I just showed that we said कि number of holes is equal to the number of impurities. Number of electrons is going to be Ni square by NH. Ni square was the product, है ना? The number of electrons is going to be Ni square by NH, and NH is going to be the number of impurities. Yeah. So that's how, if I give you number of impurities and I give you Ni, you can find how many of the minority charge carriers are left. Number of holes in this case is far greater than the number of electrons. This is a P-type semiconductor. Iska opposite is an N-type semiconductor. So N-type mein the dopants are pentavalent. Okay? Examples are phosphorus, arsenic, antimony. Okay? So these are pentavalent dopants. Compared to silicon, these have one electron more. Okay, they are going to have one electron more, and thus these are going to behave as conduction electrons. So what happens when you put in a phosphorus over here? As you can see, silicon had 4 electrons in its outer shell, which it is sharing with 4 neighbors to complete its octet. But phosphorus has 5. It is in a diamond structure, silicon मतलब वो tetrahedral structure. तो उसके पास 4 ही neighbor है. तो 4 इलेक्ट्रॉन उनके साथ शेयर कर रहे हैं, एक एक्स्ट्रा इलेक्ट्रॉन जो बच गया है, एक तो ऑक्टेट पूरा भर गया, that extra electron left is now in a way not bound to phosphorus, so this electron immediately becomes a free electron. I have written the wrong word. I have written valence BB, it should technically be CD. So this electron becomes a free electron, so this goes to the conduction band. Okay, which I said is like a conveyor belt. This guy is free to now move around the semiconductor. Okay, so these, in a way, what they do now, these are like the opposite. Instead of donating holes, they're donating electrons. These are capable of donating electrons to neighboring atoms. मतलब ये जो electron निकल गया, that is free to move around. So therefore, because they're donating electrons, they are called as donor impurities. They're called as donor impurities. Okay. By the way, when these guys have the extra electron, just so that we understand charge over here, when these guys have the extra electron, they are neutral. जब extra electron उनके साथ है, bound है, they are technically neutral. Okay, जब extra electron bound है, valence band में है, तो तब technically they are neutral. Okay, because phosphorus has those many protons as अभी जितने electrons surround it. But when these donate the electron to the conduction band, I'll correct that word. When these donate the electron to the conduction band, okay, conduction band, this atom now becomes positive. क्योंकि simple सी बात है, a phosphorus atom with just 4 outer electrons is going to be positive, because phosphorus has enough protons for 5 outer electrons, right? Phosphorus has enough protons for 5 outer electrons. यहाँ पे 4 outer electrons के कारण phosphorus positive होगा when it donates this. Okay. यहाँ पे I'm also letting you know the band gap. So band gap is only 0.05 electron volts for n doped silicon and 0.01 electron volts for n doped germanium. तो ऐसा नहीं कि I think I said कि जैसे ही phosphorus का electron आ गया तुरंत conduction band में चला जाता है. Sorry, that's not true. There is still a band gap, but that band gap is tiny. Okay, it's 0.05 compared to what the band gap was for an intrinsic semiconductor. So the band gap is quite small, and because of the temperature, it's room temperature. There's more than enough energy for this to cross that energy gap and reach the conduction band. Okay, once it does leave phosphorus with just 4 electrons, once this guy disappears, phosphorus is going to be positive. Okay. Let me also mention, I think I'm misreading this. Similarly, jab aluminum over here, when aluminum has that vacant hole, it is neutral. Aluminum with 3 electrons is neutral. When aluminum accepts an electron from the neighbor, it becomes positive. So agar ye hole bhar jata hai, it becomes negative. Agar ye hole bhar jata hai, aluminum has an extra electron. Aluminum with 4 electrons is going to be negative. Okay, so just it's going to matter a little later. When aluminum or when a group 3 atom accepts an electron and the hole gets filled, वो negative charge का हो जाएगा, और जब hole filled नहीं है तब वो neutral रहेगा. Similarly, जब यहाँ पे phosphorus extra electron देगा किसी और को, phosphorus positive हो जाएगा, और जब extra electron उसी के पास रहेगा तब phosphorus neutral रहेगा. ठीक है? All right. This statement, the नीचे जो लिखा है, that's more or less the same as we saw earlier. Number of conduction electrons per unit volume is more or less equal to the number of impurities. यहाँ पे phosphorus group 5 impurities जितने उतने conduction electrons होगा. Since the product of the concentration of holes and concentration of electrons is a constant, number of electrons बढ़ाने के कारण number of holes per unit volume कम हो जाएगा. So opposite of what we saw for p-type. So here conduction electrons are called as majority charge carriers and the holes are called as minority charge carriers in an n-type semiconductor. And again, अगर बकवास सा डाउट आ गया एग्जाम में, you know everything but you forget n type कौन सा वाला है, just remember n stands for negative, and negative मतलब electrons are negative, so n type is the one which donates electrons. P for positive, that's the one which donates holes. So p type is trivalent and n type is pentavalent. ठीक है? Number of electrons will be equal to the number of p type impurities. Number of holes will be equal to number of um, basically ni square was the product of nh ne, to nh is ni square by ne. Ne is number of impurities. So ऐसा अगर if I give you number of impurities and ni, you can find nh. In n type semiconductor, ne is a lot greater than nh. Okay, let's just do one question. Okay, just to work around with the number of electrons and the number of holes. Any doubts so far? Okay, if you have any doubt, anything you're not understanding, please ask. So question is, suppose a silicon crystal, suppose an Si crystal has 2 into 10 raised to 28 atoms per meter cube. Okay, 2 into 10 raised to 28 atoms per meter cube. This is doped with 1 part per million of aluminium. ppm means 1 part per million. It's doped with 1 part per million of aluminium. The total number of charge carriers per meter cube before doping was 2 into 10 to the power 16. Okay. Find the approximate concentration of holes and electrons after doping. Simple. Just give this a shot. Guys, when you get it, let me know. Very simple. Silicon crystal has 2 into 10 raised to 28 atoms. It is doped with 1 part per million of aluminium. Aluminum. Is that the spelling? The American spelling. The total number of charge carriers per meter cube before doping was 2 into 10 raised to 16. Find the approximate concentration of holes and electrons after doping. Come on, anyone? Nobody? डिस्कस करें. ठीक है, ऐसा क्वेश्चन आ सकता है मेंस में. Just remember कि again this is purely main syllabus. There's a reason it's not in the advanced syllabus. Main syllabus में तो मतलब this is just they're just gonna normally keep questions quite simple. ठीक है, तो है वैसे काफी अलग अलग concepts है इस chapter में, but again level of questions once you know everything is not going to be very high. इसमें simple सी बात ये है कि यार if I tell you there are 2 into 10 raised to 16 charge carriers before doping मतलब intrinsic semiconductor में 2 into 10 raised to 16 charge carriers है, तो उसका आधा is the number of electrons or holes या उसका आधा is Ni, है ना. So before doping half the charge carriers are electrons, half the charge carriers are holes. Ne and Nh are equal, so Ne and Nh are also equal to Ni. So this was an indirect way of telling you Ni. Ni is 10 to the power 16 meter per meter cube. Acha. Number of holes is the number of impurities. कितने impurities है? Simple. I'm saying it is doped with 1 part per million of aluminium. 1 part per million, मतलब 1 upon a million, 1 upon 10 raised to 6 times जितने atoms हैं. तो silicon has 2 into 10 raised to 8, 2 into 10 raised to 28 atoms per meter cube. उसका 1 million मतलब 2 into 10 raised to 22 atoms per meter cube is the number of aluminium impurities, and roughly that much is the number of holes. Got it? फिर number of electrons is Ni square by Nh. Ni is 10 raised to 16, Ni square is 10 raised to 32. Divide that by Nh. So that gives you 5 into 10 raised to 9 electrons per meter cube. Got it? Got the idea? ठीक है, ऐसा इस पेज पे, ये पेज 5 में ऊपर जो दिया है उस पे बेस्ड क्वेश्चंस न्यूमेरिकल आ सकता है. ठीक है, तो डोपिंग के पहले टोटल नंबर ऑफ चार्ज कैरियर्स बाय 2 इज द नंबर ऑफ इलेक्ट्रॉन्स और द नंबर ऑफ होल्स व्हिच इज द सेम एज Ni. डोपिंग के बाद जितने इम्प्योरिटीज है उतना होल्स होगा या इलेक्ट्रॉन्स होगा. ठीक है, तो मेजॉरिटी चार्ज कैरियर वैसे निकालेंगे एंड माइनॉरिटी चार्ज कैरियर Ne into Nh is Ni square से निकालेंगे. Got it? है doubt तो please पूछ लो. ठीक है, नहीं है, nobody says anything, I'll assume you've gotten it and I'll keep moving on. Okay, now a PN junction diode. Okay, so a PN junction diode is basically a thin wafer, okay, small thin wafer जिसका 1/2 is a p-type semiconductor. P-type has holes as the majority charge carrier, and the other half is an n-type semiconductor जिसमें free electrons are the majority charge carriers. अच्छा, इसको बनाते कैसे हैं? So one important like theoretical question sometimes is asked is, can we take a p-type junction and an n-type junction and just join them together? Okay, so we'll find that it cannot be made by just joining an n and p-type semiconductor, because in reality, no matter how flat the p-type and the n-type semiconductor may seem from outside, at the molecular level, nothing you manufacture can be perfectly flat. Okay, at the molecular level, they'll be rough, and therefore when you join them, there will be discontinuities, and those discontinuities will affect the motion of both electrons as well as holes. Okay, holes के motion के लिए you need those neighboring atoms, right? So molecular levels में disruption नहीं चाहिए. Okay, that will affect the semiconductor. So you cannot just join n and p-type semiconductors together. So how is this made? It's actually made several processes. Just to give you a brief idea, it's actually made by taking a pure intrinsic semiconductor and placing the dopants at its ends and heating them. Okay, very simple words. सादा सिलिकॉन कंडक्टर लेता है, ठीक है, उसके एक साइड पे पी टाइप लगा देता है और दूसरे साइड पे एन टाइप, और उनको हीट कर देता है. हीट करने के कारण dopants, then they start diffusing into the intrinsic semiconductor. The diffusion के through it's created. ठीक है? All right. Heating gives them energy to diffuse, and then diffusion के through it's created. Now, an ideal PN junction diode looks like this. So this side is going to be the P side, where there are a lot of holes, very few electrons. This side is going to be N side, N type, where there are a lot of free electrons. I'm representing free electrons with orange dots and holes with green circles. Okay. Now, that's a PN junction diode. What starts to happen is, first and foremost, electrons try to diffuse to the P side. है ना? Electrons try to diffuse to the P side. यहाँ पे बहुत ज़्यादा electrons है, ठीक है? So they start move. यहाँ पे है ही नहीं, right? So they start moving towards this side. So electrons try to diffuse towards the P side, and electrons का diffusion valence bond में हो रहा है. These valence band में हो रहा है. I messed this up again. Electron का diffusion conduction band में हो रहा है. Conduction. Okay. And holes का diffusion valence band में हो रहा है. ठीक? So electrons are trying to diffuse to the P side, जहाँ पे electrons नहीं है वहाँ पे जाने की कोशिश करेंगे via the conduction band, and holes are going to diffuse to the N side via the valence band. Okay. As this starts to happen, the electrons and holes will start to recombine. So once this diffusion is taking place, electrons and holes are going to start to recombine, and as they recombine, they're going to annihilate each other. Okay. So imagine this set of this electron going and recombining with this hole, this electron recombining with this hole. What are we going to be left with? So first and foremost, P-type atoms on this side, imagine aluminum, which were initially neutral, have now accepted an electron into that hole. And as they accept electrons, these are going to become negatively charged. They were neutral with the hole. Big electron aa gaya. Aluminum will now have 4 electrons. So that's going to be Al minus. It's going to become negative. When N-type atoms accept holes, so what does accept holes mean? So everyone will use this kind of language कि hole इधर जाके N-type atom hole को accept कर रहा है. Reality में actually क्या हो रहा है? यहाँ पे electron valence band के along move करके वो hole को fill कर रहा है. इसमें electrons valence band के along move करके hole को fill कर रहा है. Electrons go on the opposite side. Yes. ठीक है? तो electron वैसा जाने का effective मतलब यही हुआ कि hole N side में आ गया. P side से N side में hole आ गया. Okay. So when N-type atoms, coming back to this line, when N-type atoms accept the holes, matlab they donate their electron to a neighboring atom with a hole, what's going to happen? These guys will become positively charged. Okay. Why? Because now imagine phosphorus on the N side, instead of having 5 electrons, it has donated its electron to a neighboring hole. So now it has only 4 electrons. Whereas protons, phosphorus में 5 electron के बराबर है. 5 outer electron in that sense बराबर है. So phosphorus will now have an extra proton, 1 less electron, so it will become positively charged. So what happens is the diagram then starts to look like this. तो यहाँ से जिन्होंने अपने electrons दे दिया है, वो N-type atoms positively charged हो जाता है, और यहाँ पे जो P-type atoms ने electron accept कर लिया है, वो negatively charged हो जाता है. So you have Al minus on the left hand side and P plus, phosphorus plus on the right hand side. वैसा scene हो गया. Now, this region devoid of holes, अभी ये एक region आ गया जिसमें holes और electrons नहीं है. So this region devoid of holes and electrons, free electrons, is called as the depletion region or space charge region. This region is called as a depletion region or space charge region. Okay, because there's charge over here in this space and there's no holes and electrons. So holes and electrons have been depleted over here. Okay, hence the name depletion region. Now, because of the charge separation, ये charge separation के कारण a potential difference called barrier voltage is set up between the two sides. तो यहाँ पे एक barrier voltage set up हो जाता है. As you can see, because of this positive and negative charge, एक electric field right से left की तरफ create हो जाता है. चार्ज सेपरेशन के कारण ऐसा एक राइट से लेफ्ट एन से पी के डायरेक्शन में एक इलेक्ट्रिक फील्ड क्रिएट हो जाएगा इन चार्जेस के वजह से. ठीक है, इलेक्ट्रिक फील्ड के proportional, then you'll also have a potential difference. As the region becomes bigger, this voltage and the corresponding field becomes bigger. As this depletion region becomes bigger, the voltage starts to become bigger. Okay, if you have any doubts, guys, please ask. Okay, now as this voltage gets bigger, what's going to happen is ये जो diffusion हो रहा था, let me show you the next page. Okay, so right now at this stage, okay, as we said, there is some charge separation taking place, and electrons are trying to diffuse from the n side to the p side. So, and holes from the p side to the n side. So now, in this process, we are going to see two types of currents. There is one current called a diffusion current. Okay, what is this diffusion current? This is the current corresponding to the majority charge carriers. Okay, so as I said, electrons are trying to diffuse from n to p, holes are trying to diffuse from p to n, right? And electrons के opposite current आता है, holes के direction में current आता है, तो इन दोनों का combination means there is a current from p to n. There is ultimately a current from p to n which is taking place because of diffusion. Okay, this is due to a combination of the holes diffusing from the p side to the n side. Holes का diffusion valence band के along होता है, and electrons diffusing from n side to the p side along the free conduction band. ठीक है, तो इसके combination के कारण there is a net current. ठीक है, दोनों के कारण current is from p to n. ठीक है, so when you combine them, there is an even bigger current from p side to n side. Okay, this current from p side to n side depends on the barrier voltage. कैसे? जैसा धीरे धीरे डिप्लीशन रीजन का साइज बढ़ता है, वो बैरियर वोल्टेज बढ़ेगा. Let me see the diagram once more. So as this depletion region over here, ठीक है, as this depletion region starts to become bigger, as there is more positive and minus charge separation created, as this depletion region becomes bigger, this electric field becomes stronger. Now, this electric field is not going to let electrons go over here, because electric fields will try to push the electrons back to the n side. Similarly, this electric field is not going to let holes go over there. Okay, it's going to make it difficult for electrons and holes to go over there. So only those which have enough energy to cross this potential barrier, only those will be able to reach the other side. So क्या हो रहा है? Gradually, as this potential barrier is becoming bigger and bigger, diffusion current starts to decrease. The diffusion current starts to decrease because this barrier is preventing electrons to diffuse to the p side and holes to diffuse to the n side. Okay? By the way, both contribute to a current from p to n. Both contribute to a current from p to n. ठीक है, एक valence band में current है, एक conduction band में current है, but both are contributing to a current from p to n. Okay, so just quickly coming back, what is happening because of this? This field has a tendency to pull the electrons back to the n side and holes back to the p side. Thus, the diffusion current decreases as the barrier voltage increases. Okay, so this is one process that starts to happen. पहले diffusion हो रहा था, but gradually as that barrier is becoming big, diffusion current छोटा होते जा रहा है. एक और इस process के दौरान one more type of current gets set up, and that is called as a drift current. These concepts are important because that will help you understand what we will do later in the chapter. Drift current क्या है? you know that depletion region that was there. In that depletion region, gradually electron hole pairs will get generated. Okay, naturally electron hole pairs are going to start getting generated in the depletion region as well by thermal collisions. Okay, now this is going to be, by the way, this electron hole pair creation will be taking place because of thermal collisions only. It's not going to take place because of that electric field. Just to set some context, इलेक्ट्रिक फील्ड को इलेक्ट्रॉन निकालने के लिए बहुत ज्यादा स्ट्रॉन्ग फील्ड का जरूरत है, ठीक है। तो इलेक्ट्रिक फील्ड के कारण वो इलेक्ट्रॉन निकल नहीं रहे। इलेक्ट्रॉन्स और होल पेयर्स क्यों बनेंगे? बिकॉज ऑफ टेम्परेचर। थर्मल कोलिजन के कारण सफिशिएंट एनर्जी बनता है फॉर द इलेक्ट्रॉन्स टू गेट आउट ऑफ the atom and enter the conduction band. So when electron hole pairs, like I taught you earlier, are being created in the depletion region, what will happen is all these electrons and holes are immediately swept by the electric field. अब वो depletion region में electric field है, so they'll be swept by the electric field such that holes go to the p side. Holes go to the p side. P side कौन सा हो गया? लेफ्ट हैंड साइड। तो होल्स आर इन अ वे गोइंग टू बी, अगर इधर होल बन गया, वो होल इज गोइंग टू बी सेंट बैक ओवर देयर इलेक्ट्रिक फील्ड के कारण। और यहाँ पे जब एक इलेक्ट्रॉन साथ में क्रिएट हुआ, दैट्स गोइंग टू बी सेंट हियर इलेक्ट्रिक फील्ड के कारण। इलेक्ट्रिक फील्ड सेंड्स इलेक्ट्रॉन्स इन द ऑपोजिट डायरेक्शन ऑफ द फील्ड। तो ये इसके कारण क्या हो रहा है, जस्ट टू एक्सप्लेन ओवर हियर इटसेल्फ, होल्स अब लेफ्ट की तरफ जाएंगे, इलेक्ट्रॉन्स राइट की तरफ जाएंगे इस फील्ड के कारण। And holes left की तरफ, electron right की तरफ contributes to a current because of both of them towards the left. So this is a different type of current. Diffusion current, holes वहां जा रहा था, electrons opposite direction में जाने के कारण diffusion current right की तरफ था, P से N, और ये current left की तरफ है, N से P। ये current left की तरफ है, N से P। Okay, ये जो current मैं describe कर रहा हूँ, that's called as a drift current. Okay, that's called as the drift current. So holes and electrons created are swept by the electric field so that holes go to the p side, electrons go to the n side. Okay, and what's the difference in this motion? Technically तो motion electrons का ही होता है, as you know, even when holes move, electrons are moving, but basically holes going to the p side is motion in the valence band, मतलब the band which is bound to the atoms, and electrons moving is motion in the conduction band. Okay? This is just to give you some clarity of what's happening. तो अब क्या हो गया, यहाँ पे एक extra, the few electrons on the p side and holes on the n sides can also diffuse into the depletion region and get swept away to the other side. So the drift current उसके कारण भी होता है, जो minority carriers है, p side में थोड़े से electrons रहेंगे और n side में थोड़े से holes रहेंगे, they also may try to diffuse to the other side, है ना। तो उसके कारण भी as soon as they enter, the electric field takes them to the other side. Okay, so because of all of this, but mainly because of electron hole pairs being generated in the depletion region, we have a current which is from N to P. Okay, you have a current in the direction of that electric field created inside the depletion region. Diffusion current P से N है, drift current N से P है। ये current weak है normally, this is of the order of microamperes, and ये current is more or less independent of the size of the depletion region or the barrier voltage. Yeah, it's independent of those. It's found that it's independent of those. It's independent of the barrier voltage, especially because वो field के कारण create नहीं हो रहा है। ये जो electron hole pairs create हो रहा है, वो temperature के कारण create हो रहा है। Temperature अगर तुम बढ़ाओगे, number of holes and electrons created in the depletion region will increase significantly. टेम्परेचर बढ़ाने, टेम्परेचर के कारण हो रहा है, ठीक है। The field itself is not strong enough to free the electrons from the atom. This is not a metal. Metal में gap almost zero होता है, तो electrons immediately reach the conduction band and move away. ये semiconductor है, electric field के कारण electrons are not going to leave the parent atom. Temperature के कारण they may jump to the conduction band. That is what is happening over here. So this, and ज्यादा ऐसे electrons करते नहीं, so this current is weak. It's more or less independent of the barrier voltage. Okay, that's what we see. And this is the current due to the minority charge carriers. Okay, this is the current due to the minority charge carrier. So you have a current, to summarize, you have a diffusion current जो P से N जा रहा है, okay, P से N diffusion current जा रहा है. इसके कारण क्या हो रहा है? Holes are going to the N side and electrons are coming to the P side. But there you have holes and electrons created in the depletion region. इलेक्ट्रिक फील्ड के कारण होल्स इस तरफ जाते हैं और इलेक्ट्रॉन एन की तरफ जाते हैं. तो ये जो ड्रिफ्ट करंट है ये ऑपोजिट डायरेक्शन में है. और ये ड्रिफ्ट करंट बैरियर वोल्टेज पे डिपेंड क्यों नहीं करता है? क्योंकि वो टेम्परेचर के कारण जनरेट होता है. और जैसे ही जनरेट हो गया, इलेक्ट्रिक फील्ड कम हो या ज्यादा हो, होल तो अल्टीमेटली इलेक्ट्रिक फील्ड के डायरेक्शन में जाके अल्टीमेटली लेफ्ट हैंड साइड में आएगा. ठीक है. सो it does not really get affected much by the barrier voltage. Now, I hope you understood these terms, and in the context of this chapter, you will understand more. I know this is like new stuff, bizarre stuff, but in the context of this chapter, as we continue further, you will start to understand more. So, ये diagram में I've in a way represented our diffusion current from P to N and our drift current from N to P. Okay. Now, देखो, इनिशियली स्टार्टिंग में डिफ्यूजन करंट बहुत ज्यादा है. ठीक है, क्योंकि पोटेंशियल बैरियर कम है. इलेक्ट्रॉन्स वांट टू गो देयर, प्रोटॉन्स, होल्स वांट टू गो हियर. दे वांट टू मिंगल एंड दे वांट टू गो टू द अदर साइड. सो स्टार्टिंग में डिफ्यूजन करंट कम है, ज्यादा है, और बैरियर बहुत कम है. The drift current on the other hand is small and it's always more or less constant, as I already mentioned. अब ग्रेजुअली क्या होता है? डिफ्यूजन करंट बिकॉज ज्यादा है, बिकॉज इट्स मोर, बिकॉज द डिफ्यूजन करंट इज मोर, you start to have this charge separation taking place. Remember, diffusion current means holes are going there, so N side is losing electrons, P side is losing, is getting the hole filled. Therefore, P side में negative charge आता है, N side में positive charge आता है. Diffusion current के कारण ये depletion region बड़ा होने लगता है. Depletion region बड़ा होने लगता है. Okay. Now, as the diffusion current is more, the width of the depletion region increases. As that increases, the barrier voltage starts to increase. Barrier voltage क्या करता है? Diffusion current को धीरे धीरे oppose करना start करता है. So it's like slowly that diffusion current starts decreasing. It starts decreasing because of the barrier voltage. Barrier voltage बोल रहा है नहीं, hole तो जा नहीं सकता वहां पर. ठीक है. So therefore the diffusion current starts to decrease. Now, this process will go on till the diffusion current becomes equal to the drift current. Till diffusion current and drift current become equal. Drift current constant है, कम है. Diffusion current starting में बड़ा है, उसके कारण ये depletion region बन रहा है. But gradually depletion region ही diffusion current को oppose करके gradually वो diffusion current कम होके अंत में क्या हो जाएगा? Drift current के बराबर हो जाएगा. Drift current के बराबर हो जाएगा. Right? At this instant, equilibrium is attained and there is no net current across the junction. This is kind of like terminal velocity. You drop an object in the fluid, तो पहले तो है ना वैसे ही है ना, ग्रेविटी के कारण ये नीचे जा रहा है, एंड तुम्हारा ये जो है इन अ वे इट्स समवन लाइक दैट. तुम्हारा विस्कस फोर्स पहले कम है, बट एज स्पीड इंक्रीजेस विस्कस फोर्स बढ़ के जाता है, देन इट कैचेस अप विद ग्रेविटी. यहाँ पे इन अ वे थोड़ा उल्टा है. यहाँ पे ड्रिफ्ट करंट कम है और स्टार्टिंग में ये डिफ्यूजन करंट ज्यादा है, जिसके कारण डिप्लीशन रीजन बड़ा होते जा रहा है. बट एज डिप्लीशन रीजन बड़ा होता है, डिफ्यूजन करंट छोटा होते जाता है, एंड इवेंचुअली डिफ्यूजन करंट एंड ड्रिफ्ट करंट बराबर हो जाता है. So it's not a static process, it's a dynamic process. Even when equilibrium is attained, there is no net current across the junction, but electrons and holes are still diffusing, drift is still taking place. It's just that they are in equal amounts, more or less, which is why there is an equilibrium. Okay. And sometimes you see this kind of diagram in a textbook, which is just showing you how potential varies with X. So as I start from this side, and then as I enter this charge separation region, as I go to the positive side, I will see an increase in potential. And then uske baad again neutral atoms, so the potential is more or less constant. So that increase in potential is called as the potential barrier of that region. This is a PN junction diode. Any doubts so far? Okay. Now, this diode is going to get connected to a battery. So when we connect this diode to a battery in such a way that the positive terminal of the battery is joined to the P side. P side को positive terminal के साथ join करोगे तो it's said to be forward biased. Okay, imagine P to P, N to N. P side to the positive terminal, N side to the negative terminal. P to P, N to N. वैसा. So when you connect it that way, it's said to be forward biased. अच्छा, क्या हो जाएगा when I connect this battery? So quickly just explaining the setup. When a battery is connected with its positive terminal attached to the P end of the junction, it is said to be forward biased. Okay. Now again, this explanation, I'm just, you can imagine, you can remember what finally happens. But again, this explanation is just to tell you why things happen, because a lot of times students start to have these doubts. Some things just, when you think about, sometimes they don't make sense. Sometimes I'm going to explain to you why what we observe happens. So as soon as I connect this battery, as indicated above, the battery starts pulling electrons from the negatively charged P side depletion region. Okay, it starts pulling electrons to the negatively charged. Yes, Devin, yes. P side depletion region along the valence band to the positive terminal, thus making the holes move further in. Okay, thus making the holes move further in. So let me explain what is happening. Thus. Okay, तो क्या हो रहा है? ये बैटरी के कारण है ना, इलेक्ट्रॉन्स आर अट्रैक्टेड टू दिस पॉजिटिव प्लेट. सो क्या हो रहा है यहाँ पे, जो अब एक तो नेगेटिवली चार्ज एटम्स है, ठीक है, these are all those aluminum atoms जिनके electrons are filled. So those electrons, they start moving along the valence band itself. ठीक है, इलेक्ट्रिक फील्ड बैटरी के कारण इतना फील नहीं आता है कि ये इलेक्ट्रॉन कंडक्शन बैंड में जंप करेगा, बट वो वैलेंस बैंड के अंदर ही होल टू होल ऐसा जंप 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 करके फिर वायर एंटर करके पॉजिटिव टर्मिनल की तरफ भागता है. ठीक है, फिर नेगेटिव टर्मिनल यहाँ से उतने ही इलेक्ट्रॉन्स देता है, और वो इलेक्ट्रॉन्स, ठीक है, वो इलेक्ट्रॉन्स भी अभी सिमिलरली मूव करके दे अगेन recombine with the n-side atoms. So they again enter the valence band of the n-side atoms. So what is happening over here is, यहाँ से इलेक्ट्रॉन्स हटा के यहाँ वापस दिया जा रहा है, जिसके कारण ये बैटरी के कारण हो रहा है. जिसके कारण क्या हो रहा है? Okay, let me read that line. The battery then supplies electrons to the positively charged n-side depletion region along the conduction band, and then when they recombine, it's now again bound to the atom with the energy gap being very little. But यहाँ पे हाँ, conduction band के along भेज के then it recombines with the atom over there. Ultimately, what has happened over here is, you now, because these electrons have come here, you find कि holes are effectively moving in. तो left hand side से holes अंदर जा रहा है, और right hand side से electrons अंदर आ रहा है. So as indicated on the next page, this is going to cause the depletion region to become small, and this is going to cause the barrier potential to decrease. Okay, the depletion region is going to become small and the barrier potential is going to decrease. Okay, some people trying to explain it by saying this battery is opposing that electric field, therefore it's becoming small. But in reality, this is actually what is happening. The battery is decreasing the size of the depletion region. वो ऐसे electrons को यहाँ से खींच के यहाँ से लेफ्ट हैंड एक से ना, सॉरी, यहाँ से इलेक्ट्रॉन्स को खींच के इधर डाल रहा है, जिसके कारण ये डिप्लीशन रीजन छोटा हो रहा है, और डिप्लीशन रीजन छोटा हो रहा है, देयर आर फ्यूअर चार्जेस नाउ, सो योर बैरियर पोटेंशियल आल्सो इज गोइंग टू डिक्रीज. ओके, जिसके कारण क्या होगा, एज अ रिजल्ट ऑफ दिस द डिफ्यूजन करंट इंक्रीजेस अबाउट द ड्रिफ्ट करंट. किसको बैरियर के कारण प्रॉब्लम था? डिफ्यूजन को बैरियर के कारण प्रॉब्लम था. ड्रिफ्ट करंट ज्यादा कभी चेंज होता ही नहीं है. ड्रिफ्ट करंट ओनली डिपेंड्स ऑन टेम्परेचर. So because of this battery, we are making this barrier only small. Okay, this is, इसको मैंने कैसा लेबल किया है, VBI, I for initial. So this is the initial barrier voltage. बैटरी क्या करेगा, इसको छोटा कर देगा, जिसके कारण डिफ्यूजन का रेट बढ़ेगा. ड्रिफ्ट का रेट लगभग उतना है, डिफ्यूजन का रेट बढ़ गया. The net current through the junction is thus diffusion current minus drift current. बैटरी के कारण there is now a net current from the P side to the N side. This is a forward based, this is how a forward based PN junction diode works. Okay, if you have any doubts please ask. So I've shown you the diagram, now the next page. So finally ऐसा होगा, वो बैटरी के कारण ये डिप्लीशन रीजन छोटा हो गया, डिफ्यूजन करंट बड़ा हो गया, ड्रिफ्ट करंट लगभग पहले जितना ही है, but diffusion current is now a lot bigger than the drift current, which is why there is now a net current from P to N. There's now a net current from P to N. This final barrier voltage is smaller than the initial value. Okay. In fact, my final barrier voltage is my initial barrier voltage minus some value. And वो जितना जो value जितना वो पोटेंशियल से इनिशियल पोटेंशियल फाइनल पोटेंशियल इनिशियल पोटेंशियल से जितना कम हो रहा है, I've represented that as Vj, and Vj is the potential difference due to the battery at the junction. बैटरी के कारण वो पोटेंशियल डिफरेंस कम हो रहा है, ठीक है, जंक्शन पे. Okay, this is our forward bias PN junction diode. Now यहाँ पे at this page, ठीक है, there is some theory. I'll just quickly read through it, but this beach wala part is just for your reference. Okay? This is just for your understanding. If somebody has some doubts, if somebody feels what is explained just by itself doesn't make sense, a little bit of this will help you understand that. You don't have to remember exactly what I've written inside these brackets, but they are for reference. Somewhere down the line, when you have some doubts, you may find the answers to that in this. ऊपर नीचे ऑफ कोर्स बोल्ड में लिखा है, तो इंपॉर्टेंट चीज है. तो पहले तो ये जो मैंने बोला डिफ्यूजन करंट, वी फाइंड दैट दिस डिफ्यूजन करंट increases exponentially with E, not linearly but exponentially. It increases exponentially with E. It's actually an exponential function. Okay, so it increases exponentially with the battery and therefore becomes significantly large once E becomes greater than a voltage called as the cut in voltage या threshold voltage. क्या याद करना है, ये जो अपना करंट है फॉरवर्ड बायस में, वो बहुत तेजी से बढ़ता है, बट इट्स सेड कि वो तेजी से एक वैल्यू के बाद बढ़ता है, एंड दैट वैल्यू इज कॉल्ड एज द कट इन वोल्टेज और द थ्रेशोल्ड वोल्टेज. कट इन वोल्टेज और थ्रेशोल्ड वोल्टेज. ओके, दैट इज व्हाट इज स्टेटेड. ठीक है, that's what you have to remember. But doing a lot of research online, I realized this is what we have discovered. Actually the cut-in voltage is just approximated graphically from the exponential curve. This exponential curve, it keeps increasing steeply. So just graphically they determine, अच्छा ये point के बाद लग रहा है कि ग्राफ वो तेजी से rise हो रहा है, and that's how they define the cut-in voltage. Okay, the cut-in voltage is when you change the scale of the graph accordingly, even the cut-in voltage is normally technically changes. Okay, this cut-in voltage increases with the barrier voltage. Logically जितना बड़ा barrier voltage होगा उतना ज्यादा तुम्हें है ना opposite direction में accordingly ज्यादा बड़ा voltage डालना पड़ेगा to oppose that barrier voltage. तो जितना बड़ा barrier voltage उतना बड़ा cut-in voltage, after which you see significant current. So it's somewhat close to it, but it is not the same thing. It's not equal to the barrier voltage. Okay, it's not equal to the barrier voltage. Again, just for your information. Semiconductors, all those who are going to take electrical engineering later on as well, this is in that sense an important chapter. So while certain things may just, it may help you to just remember basic things the way they're taught, but then they're not fully exactly true. So you need to At least later on, you can refer to these notes if you're going to pursue electrical engineering further. And this may take place of certain misunderstandings that you get when you just read a textbook. So contrary to common misunderstandings, no drastic change in mechanism takes place once the battery voltage crosses the initial barrier voltage. बहुत लोग को लगता है कि अगर barrier voltage 3 वोल्ट है तो मैं 3 वोल्ट का बैटरी से ज्यादा वोल्ट मतलब 4 वोल्ट का बैटरी यूज करूंगा तो है ना बहुत ज्यादा करंट दिखेगा. That's not exactly what happens inside the semiconductor. There's no drastic change when the battery ka voltage crosses the barrier voltage. In fact, it's found that the barrier voltage never becomes zero or negative. That field is always inside the semiconductor is always from N to P. That never gets opposed. Okay? Again, that's just for your information. I'm just going to read it once and not dwell on it. It's because it never becomes zero unless the battery is very, 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 very large. Because क्या होता है, as the battery's EMF increases, large currents start to flow. Large currents के कारण क्या होता है, potential difference across the P and N side becomes significant. ठीक है, तो ये जो P and N side है, they are also going to have some resistance, right? Let's say the resistance is Rn and Rp. तो as बैटरी का साइज बढ़ाओगे तो उस इनके अक्रॉस भी ड्रॉप सिग्निफिकेंट हो जाता है. तो उसके कारण क्या हो रहा है, पोटेंशियल ड्रॉप ड्यू टू द बैटरी अक्रॉस द जंक्शन इज अ लॉट लेस देन ई. ये नहीं है कि बैटरी तुमने ई का डाल दिया तो यहाँ पे बैरियर वोल्टेज ई से कम होगा, नहीं ना. एज करंट बढ़ेगा यहाँ पे भी ड्रॉप होगा, यहाँ पे भी ड्रॉप होगा. तो अक्रॉस द डिप्लीशन रीजन ड्रॉप उतना ज्यादा नहीं होगा. ड्रॉप मैंने बोला था VJ, we are calling the drop due to the battery VJ, and VJ is going to be a lot less than E. Unless it's found that unless E is very, very large, this drop at the depletion region is normally lesser than the barrier voltage. So there will always be some barrier voltage and depletion region ka width will always be present. Okay? As the holes on the P side will always accept conduction electrons from the N atom. So basically, तुम ये बैरियर को वैसा कभी गायब नहीं करा सकते हो. ऐसा नहीं कि बैरियर वोल्टेज 3 वोल्ट है तो तुम 4 वोल्ट का बैटरी यूज कर लो तो बैरियर ही गायब हो गया, ऐसा नहीं होता. Okay, that diffusion process is always going to take place. So always a barrier is going to get created. As तुम बैटरी का EMF बढ़ाते जाओगे तो यहाँ पे ड्रॉप भी सिग्निफिकेंट होते जाता है. तो बैटरी के कारण यहाँ पे जो पोटेंशियल ड्रॉप हो रहा है वो उतना सिग्निफिकेंट नहीं होता है, and it does not overcome the barrier voltage. That barrier voltage the barrier does not disappear unless E is very, very large. To fight the entire nature of diffusion itself, उतना बड़ा E है, only then your barrier will disappear. So just remember that. Okay? This entire passage, if you want, you can read again later. You don't need to remember it, but the point of this passage is 3 volt का barrier voltage अगर है, you cannot make the barrier disappear by using a battery of greater than 3 volt EMF. It does not disappear like that. Okay, the barrier voltage will always be there. Okay. That said, these are some facts. Okay, but अभी कई बार ऐसा एग्जाम में क्वेश्चन आता है, अगर न्यूमेरिकल पूछा है, ठीक है, एंड बैटरी का EMF मान लो बैरियर वोल्टेज से कम है, मतलब P से ये जो बैरियर वोल्टेज है मान लो ऐसा 3 वोल्ट दे दिया, ठीक है, और बैटरी का EMF उन्होंने दे दिया मान लो 1 वोल्ट, ठीक है. ओके, देन एंड इफ दे आस्क यू कि अब बैटरी के कारण अब यहाँ पे नेट बैरियर वोल्टेज कितना हो गया, अगर ऐसा न्यूमेरिकल आ रहा है, प्लीज डू 3-1. बोल दो कि ये 1 वोल्ट के कारण क्या हो जाएगा, ये 3 वोल्ट वाला EMF कम होके 2 वोल्ट हो जाएगा. तो तब यूज फाइनल वोल्टेज इज इनिशियल वोल्टेज माइनस EMF. दिस इज अज्यूमिंग कि बैटरी के कारण पूरा का पूरा 1 वोल्ट वहीं पे ड्रॉप हो रहा है. स्टार्टिंग कम करंट के केस में दैट्स देयर, बट एज द बैटरी बिकम्स बिगर, ऐसा नहीं है कि ये 4 वोल्ट है तो 4 वोल्ट का ड्रॉप वहां पे आएगा. एज द बैटरी बिकम्स बिगर, ठीक है, and it approaches 3 volts, current starts to increase really fast. as the current starts to increase really fast, पूरा बैटरी का EMF जो है अब वो यहाँ पे गिरना स्टार्ट होता है, and it's not going to drop only across the depletion region. Okay, so technically, I mean, this is not true technically. Okay, this is not true. बैटरी के है ना, बैटरी के current drop sides के along भी होता है. But if they ask you a numerical, just do this. ठीक है, if they ask you a numerical like this, बैटरी का वोल्टेज कम रहेगा 1 वोल्ट 2 वोल्ट, और डिप्लीशन रीजन का वोल्टेज ज्यादा रहेगा 3 वोल्ट, ऐसे कुछ दे देंगे, एंड फाइनल वोल्टेज कितना हो गया फॉरवर्ड बायस में, then just subtract. ठीक है, just do it that way. ठीक है, if the question is asked after what voltage, ऐसा भी अगर the question is asked after what voltage the current starts to increase exponentially in a forward bias diode, just answer it's the cut in voltage. Theoretical सवाल आया, कितना वोल्टेज के बाद current increases exponentially, it's the cut in voltage. Though I said ऐसा कुछ जादू नहीं होता है cut in voltage के बाद, it's always increasing at an exponential rate in reality. Cut in voltage is just a graphical tool जिससे हम बोलते हैं चलो एक point के बाद we'll say this rate is significant, but ठीक है, that's for your information. They ask किस point के बाद current suddenly increase होता है, you just say okay fine, they're talking about cut in voltage. Cut in voltage के बाद significantly increase होता है. Mechanism wise, nothing really. The mechanism doesn't change magically. Okay, at that cut in voltage. It's just after that voltage, the rate is significant. All right. So this page was just like a little bit of information. That's basically now just give you an idea of what happens in a forward bias. Okay. Now quickly, just explain what happens in the reverse bias. Just 1 or 2 pages. Reverse bias में हम क्या करेंगे, बैटरी को हम उल्टा कनेक्ट करेंगे. The reverse bias में N side of the battery is connected to the positive terminal, P side is connected to the negative terminal. इसके कारण क्या होता है, as you have already understood, now this time opposite होगा and depletion region बड़ा हो जाएगा. क्यों? As you can see, this battery is going to pull electrons, okay, to the positive terminal from the N side, and these same number of electrons are going to go from the negative terminal to the P side, and these electrons are then going to keep hopping in the valence band, and they're going to finally fill up the holes over here in the P side. Right? We'll fill up the holes over there in the P side. So what is going to happen because of this? यहाँ से electrons हटाना मतलब यहाँ पे positive create करना. तुम phosphorus से electrons हटा रहे हो तो यहाँ पे positive region extra आ जाएगा, और यहाँ पे electrons हटाना मतलब you are filling up these holes, तो यहाँ पे aluminum has an extra electron, यहाँ पे negative region आ जाएगा. So a reverse bias battery tries to increase the size of the junction. The reverse bias battery will increase the size of the junction. So what happens when a battery is connected with its positive terminal attached to the N end of the junction, it is said to be reverse biased. As indicated above, the battery starts pulling electrons, conduction electrons, to the N atoms close to the depletion region, making these atoms positive. So यहाँ पे ये electrons को भी positive मतलब ये atoms को भी positive करेगा because वहाँ से electrons हटा रहा है. To the positive terminal, it sends these electrons to the positive terminal, and from these go to the positive terminal. Then from the negative terminal, it supplies electrons to the holes in the P atoms, ye holes, close to the depletion region, making them negative. So यहाँ पे ultimately ये hop करके यहाँ पे settle हो जाएगा, वो region भी negative हो जाएगा. So as indicated on the next page, this causes the size of the depletion region and the barrier potential to increase. ठीक है, तो reverse bias में depletion region बढ़ा होता है, barrier potential कम होता है. This decreases the diffusion current below the drift current. तो barrier potential बड़ा होने के कारण क्या हो रहा है, diffusion current और छोटा हो गया. Remember, unbiased में diffusion and drift are the same, but in reverse bias, diffusion current becomes smaller because of the bigger depletion size. Diffusion current becomes smaller than the drift current. Drift current stays the same always unless temperature changes. So the net current through the junction is thus drift current minus the diffusion current. Drift current minus the diffusion current. So this is the diagram. तो रिवर्स बायस में ऐसा सीन हो जाता है, ठीक है. द डिप्लीशन रीजन बिकम्स बिगर, डिफ्यूजन करंट छोटा हो गया बिकॉज बैरियर बहुत बड़ा हो गया. ओनली फ्यूअर diffusing holes and electrons have the energy to cross the barrier now. Okay? But drift is more or less the same. Okay? I've just shown it with the bigger arrow to in a way say that drift is bigger than diffusion. Drift has not changed, never changes. Diffusion has of course decreased. My final barrier voltage is initial barrier voltage plus the whatever the battery is giving to the junction. तो बैटरी के कारण, ठीक है, बैटरी के कारण यहाँ से यहाँ एक पोटेंशियल चेंज आ रहा है, ठीक है. My final barrier voltage is the initial barrier voltage plus the potential difference supplied by the battery between P and N. Now इसमें क्या होता है, reverse bias में current is typically very small. Because current is typically very small, क्या होता है, these terms बैटरी के कारण जितना ड्रॉप रेजिस्टेंस के कारण होगा वो बहुत कम होगा. Okay, remember the net current is drift current minus diffusion. Drift itself is of the order of microamperes. So reverse bias में current actually काफी छोटा होता है. काफी छोटा होने के कारण ड्रॉप अक्रॉस द रेजिस्टर्स इज वेरी स्मॉल, जिसके कारण लगभग ये पूरा जो बैटरी के कारण यहाँ पे जो पोटेंशियल ड्रॉप दिखना चाहिए, यहाँ से यहाँ ई चढ़ा, यहाँ से यहाँ ई गिरेगा. कहाँ पे गिरेगा, करंट बहुत कम है तो इतने रीजन में नहीं गिरने वाला है. कहाँ पे गिरने वाला है, इसके अक्रॉस ही गिरेगा. तो दैट एंटायर ड्रॉप नाउ ऑफ द बैटरी कम्स फ्रॉम एन टू पी. तो पहले से बैरियर वोल्टेज है, उसके ऊपर अब ये बैटरी का भी वोल्टेज आ गया, जिसके कारण योर नेट बैरियर वोल्टेज बिकम्स इनिशियल बैरियर वोल्टेज प्लस EMF of the battery. Okay, because this term is very small, the drop provided by the battery across this region is the EMF of the battery. So forward bias में basically अगर numerical आ गया, forward bias में से VBF is VBI minus E and reverse bias में से VBF is VBI plus E. Okay. Although forward bias के लिए it's not technically true when E is very big, ठीक है, never becomes negative. VBF never becomes negative, but normally they'll keep E small and they'll ask. So just do VBF is VBI minus E if they ask. Okay, this is what happens in reverse bias. So last 10 minutes. At least let's do this page. या तक कोई doubts है क्या किसी को? Have you guys in a way followed? This has a lot of, in that sense, it has a lot of theory. And thing is, as I said, this is not similar to any mechanism we have done before, right? There's hardly any chapter which, in a way, prepared us for this. It's all new stuff. It's a new mechanism by which current is flowing. Okay? But these concepts will help you solve questions on semiconductors. Okay? Just make sure you have to understand it once. Okay. Quickly, please, let's do this page. So this is a graph. This is called as the IV characteristics of a PN junction diode. IV मतलब current and potential. So ये current versus potential का graph होता है, okay, of a PN junction diode, और ये बताता है कैसे junction के through current and potential change होता है. अभी इसमें just to explain, the drift current stays the same and so this is still reverse bias. Drift current stays the same as I said, and as the barrier increases, the diffusion current decreases exponentially. Okay, जिसके कारण reverse bias में the net current, as the diffusion current decreases, the net current starts to approach a constant value called as the reverse saturation current. Net current कितना है? Drift minus diffusion, and reverse bias में diffusion current starts decreasing. As you use a bigger and bigger battery, diffusion current becomes smaller and smaller. Okay, so decreases exponentially with the applied voltage. With the applied EMF. Okay, Alright, so finally you see कि ये जो reversed current है, ठीक है, it starts to approach a particular value. So यहाँ पे y-axis is actually telling me the current. Okay, this section of the graph is talking about reverse current and reverse voltage. तो क्या होता है, as मैं reverse voltage बढ़ाते जाता हूँ ना, you start to see कि the current is increasing starting में, but then it quickly attains a constant value. So reverse bias में current is more or less constant, and that constant value is called as reverse saturation current, and it depends from material to material. It's normally around 10 microamperes. बट एक पॉइंट में क्या होता है, रिवर्स बायस में एक सर्टेन वोल्टेज के बाद breakdown takes place, and I'll talk about the mechanism in the next class. But after a certain high voltage called as the breakdown voltage, the diode suddenly becomes conducting. This is an important region. So एक breakdown voltage के बाद the diode becomes highly conducting, and even a slight increase in voltage causes the current to increase by a lot. So इस region में after the breakdown, without any change in voltage, you are going to see very large changes in current, because this become very highly conducting. This become highly conducting. Okay, hardly any change in voltage, but a lot of change in current. ठीक है, resistance अब एकदम almost zero के आसपास हो जाता है in the breakdown region. Breakdown region में, just to tell you, there is nothing destructive about the breakdown voltage. ऐसा नहीं कि silicon damage हो रहा है, तुम हाई EMF अगर निकालोगे, it will restore the normal functioning of the diode. So this breakdown voltage is also something that is used intentionally in circuits in smart ways. बड़ा EMF निकाल दो, it will again come back to the normal region. Okay, on the right hand side, just to explain, as you can see, the graph is exponentially increasing. ठीक है, तो तुम voltage, forward bias voltage बढ़ाते जाओ, accordingly forward current बढ़ते जाएगा. ठीक है, डाउन मींस बैकवर्ड करंट एंड लेफ्ट मींस बैकवर्ड वोल्टेज, और यहाँ पे फॉरवर्ड बायस वोल्टेज बढ़ाओगे तो फॉरवर्ड करंट बढ़ते जाएगा. इन सच ग्राफ्स प्लीज look carefully at the units. Okay, this is in volt, this is in milliamperes. So as I start using batteries of 0.2, 0.4, 0.6 volts, very small forward voltage, I quickly acquire large currents. Look at the scale, 80 milliamperes के बारे में बात कर रहे हैं. Large in comparison to reverse bias. Reverse bias में voltage का size देखो 20, 40, 60, ठीक है, और current का size देखो 10 microampere. So this reverse current is a lot lesser than the forward current. Lot lesser. Okay. Cut in voltage graphically मतलब ऐसा cut in voltage technically ऐसा 0.4 या 0.6 ऐसे कुछ आएगा, ठीक है. So cut in voltage is also very small. Very soon this current starts to increase rapidly. Very soon it starts to increase rapidly. ठीक है. You won't have to ever find cut in voltage from the graph. Over here I also want you to see breakdown voltage कितना बड़ा है. 80 volts कितना बड़ा है in comparison to the forward voltages that you use. 80 volts के order में. So even as you may remember the shape of the graph, you don't have to remember values. Okay, of course, all depends on finally which material is used, silicon, germanium, which dopant is used. But the overall idea, just at least in the back of your mind, remember कि units कैसे हैं. Here the voltages are small, and you see large values of current. Current is in milliamperes. Here the voltages are large, and you hardly see current increase for a significant time. Hardly current increases. ये 10 भी microampere तक ही पहुंच रहा है. 80 volts के आसपास current has only increased till 10 microamperes. After that, suddenly breakdown voltage cross करने के बाद you start to see the current increase rapidly. Okay, so that's what we have. Yeah, that's a little bit of. I think we can stop at this place. Our next lectures next week. Most probably, I don't know if you guys are. Most likely, I don't think you guys are gonna come in the next week. But I mean, if they do schedule the lecture for lack of time, and we also have to finish the portion as such. So we do schedule, even if you guys come, it'll be great. Even if guys don't come, I'll still, we take the lecture, I'll record it 2 hours, jitna bhi time hai, 2 hours ka, I'll speak for 2 hours, I'll record it, and I'll share it with you guys. You can watch once your boards are done. Okay. This topic is significant for your mains exam. You have 4 attempts. Most likely your mains exam is going to be in the last week of Feb. Dates are not out yet. That's a tentative date. And looking at what's happening with the Omicron virus, it may get postponed further. So you will have sufficient time. Do your boards well. Okay. You will have sufficient time to cover up what you're going to miss during the boards. But yeah, if I have a lecture in the timetable, I will teach for 2 hours, even if it's just a few of you, but I'll record it and I'll ask you guys to see it and cover. Normally, this is one chapter. It's a little difficult to self-study on your own. So please do watch the recording once at least. Okay. All right. Okay then, guys. Bye-bye. If you have anything you want me to repeat today from what I taught today, please let me know. Let me know. Okay? Bye-bye.